I'm Eric Shidley, and this is Astronomy Fundamentalized, Lecture 12, The Sun. In this lecture, we'll discuss all of the critical properties of our Sun, our first test case in understanding all of the stars in our universe. Naturally, our sun is the most prominent object in the sky, and ever since man began a recorded history and a social evolution, the behavior of the sun in the sky, its rising and setting, its seasonal changes, and the manner in which it provides energy for the growing of crops and the survival of life on this planet, it's held a great fascination. But it's also important to recognize that the sun plays an important role in astronomy in the sense that it is the one star in the universe that we have close access to. That is, it's near enough to the Earth that we can make careful study of its behavior over time, telescopically observe its surface, and understand all of its very subtle properties that we would not be able to observe in stars that are much, much further away. Speaking of far away, our own sun is 93 million miles away from Earth. That's about 150 kilometers. To get an idea of the distance, I'd like you to imagine that the sun is the size of a basketball. On that scale, the Earth is about the size of the head of a pin. To get an idea of the distance between them, imagine that this basketball representing the sun and the pin representing the Earth are separated by 100 feet. Indeed, the sun is fantastically larger than the Earth, and in fact, about 100 Earths would be necessary to span the diameter of the sun. And if the sun were hollow, about 1 million Earths would fit inside. The mass of the sun is also extraordinarily large, about 10 to the 30 kilograms. In fact, not only is the sun the most massive object in our solar system, but if we were to combine the mass of everything else in our solar system, all of the planets and asteroids and comets put together are in the neighborhood of 1% of the mass of the solar system. The other 99% of the solar system is the sun itself. The temperature of the sun is also extraordinary. Temperatures in the core of our sun rise in the neighborhood of 10 million degrees. The temperature of the surface of the sun is 5,800 degrees, whereas the corona, the cloud of gases around the exterior of the sun, have temperatures from 1 to 2 million degrees Kelvin. And so there's obviously a tremendous range in temperature as well. When we look at the sun more closely, we discover that there are details to its structure and its behavior, and it's these details that are the subject of this lecture. The effective surface of the sun is referred to as the photosphere. This inset diagram that we see here shows that under close inspection, the surface of the sun appears granular. A close-up of the granules in yellow is certainly peculiar at first glance and perhaps a little bit difficult to understand. There's a way of discussing this that I've described to many people in the past, this behavior of the photosphere. In that when I go to a diner that serves coffee, I'm actually well known for doing this. Despite the fact that I enjoy drinking my coffee black, I tend to pour cold creamer into the coffee very carefully down the side so that it sinks to the bottom, leaving the surface of the coffee still black. As the creamer goes to the bottom of the coffee, it heats up and rises to the surface in clouds that begin to rise in the center. If I'm patient enough to allow this process to continue, I suggest patience because it can take as much as 15 minutes, the cream will rise to the surface where it will cool and then fall again to the bottom of the coffee. The temperature difference between the hot coffee and the cold cream sets up currents in the coffee, and these currents loop around next to each other and form what are known as convective cells. This is the process of convection, warm material rises, cold material falls. Well, the regions that we see here on the photosphere, the granules, are actually convective cells. In the center of any given convective cell, warm material is rising to the surface of the sun, and on the edges, the dark regions, the cooled material, having given up its energy in the form of light, which travels through space and ultimately arrives at Earth, giving us the benefit of its energy. These cooler regions then sink downward through an entire convective layer that exists at the surface of the sun. On the lower left, we see a fluid dynamic description of how one of these convective cells could have taken place. Also in this picture, we see a very good example of sunspot activity, which I'll come to in a moment. Above the photosphere of the sun's visible surface, there's a lower atmospheric level called the chromosphere. The chromosphere heats up by the energy that's given to it by the photosphere and emits the incandescent light which comes to the Earth and is the light that we receive. Beyond the chromosphere is the corona. The corona is a stream of ionized gas outside of or above the surface of the sun that cannot generally be seen unless the sun and the chromosphere are obscured. Common situation where the sun is obscured is during a total solar eclipse. Here we see the moon in front of the sun causing an eclipse, and we might expect the thing to go entirely black, but in fact we see this region around the sun with very bright white, and this is the corona, the ionized gas is being given off. As I said previously, the corona has a temperature of about 1.5 to 2 million Kelvin. So these ionized particles around the sun here are very, very high in energy. In fact, some of them are so high in energy that they have enough velocity to escape the sun's gravity entirely. This is the phenomenon that's known as solar wind. Streaming outward in all directions from the sun constantly is a stream of charged ionized particles that are associated with the sun's corona. This is the same solar wind that affects the behavior of the tails of comets and causes a comet's ion tail to always point away from the sun. The sun has periods of strong activity and weak activity. We call a sun where there is very little surface activity a quiet sun, and a sun where there is a great deal of surface activity an active sun. The active sun is characterized by many sunspots, prominences, and eruptions on the surface that eject a lot of charged particles into space and are associated with aberrations in the sun's magnetic field. Sunspots are the number one example of this. Observations of the sun indicate clearly that from time to time there are dark regions on the surface shown here. On the left we see an image of the sun where clearly there are black spots on the surface of the sun, and here we see a close-up of the photosphere where we can again see the granularity but a dark region that almost looks like a hole punched in the sun. There's one aspect to this that we have to bear in mind, that these dark spots of the sun are so dark that we might imagine that they're a little section of the surface of the sun that is cooled to the point where it is turned black. The reality is that this is sort of a photographic image effect here. The surface of the sun where sunspots appear is not so cold that it is not giving off any light anymore. It's not that bright. It's just that in contrast, it is significantly less bright than the surrounding photosphere. So in contrast, in comparison, it is much darker. In fact, the sunspots are quite hot, but it is true that a sunspot temperature is lower than the surrounding temperature of the photosphere. It's all in the neighborhood of 5,800 Kelvin. Sunspots are caused by peculiarities in the magnetic field of the sun. As the sun rotates on its polar axis, the magnetic field gets drug along with it. You have to bear in mind always that the sun is a fluid object. In fact, the sun rotates faster at its equator than it does at the poles. So as the material of the sun, which ultimately creates its magnetic field, rotates around, the magnetic field gets bent and twisted, and in some cases, the magnetic field lines of the sun can be pushed through the photosphere of the sun, such that the magnetic field lines extend through the surface. When this happens, the very, very dense magnetic field lines at the surface prevent the rising of warm material to the photosphere. This creates a region on the surface of the sun which is cooler and thus creates a sunspot. On the lower right here, we see a photo that shows the curves of the magnetic field lines. Now, these magnetic field lines aren't visible, but the charged particles which are ejected from the surface of the sun are forced to follow those magnetic field lines, and it makes it possible for us to get a visualization of this behavior when we take images of the sun. One of the very interesting things about sunspot behavior is that it's periodic. Every 11 years, the sun goes through a sequence of greater sunspot activity. And this is accompanied by great changes in the sun's magnetic field. In fact, every 11 years, the sun's north pole becomes the south pole. The pole literally reverses on an 11-year cycle and is back again in another 11-year cycle. This span of 22 years is often referred to as the solar cycle. We recently had a solar sunspot activity maximum in the year 2000, and now as I give this lecture in 2009, we're coming out of a minimum, and we're looking forward to greater sunspot activity in the future. When sunspots take place, when that start of the sunspot cycle begins, and we see sunspots begin to appear, we see them at high latitudes on the sun, and as the sunspot activity cycle proceeds, the sunspots appear closer and closer to the solar equator. This is related to the modification of the sun's magnetic field due to the fact that the equator rotates faster than the poles. It's not an inaccurate sort of impression to get that as the solar equator rotates more rapidly, it drags the sunspots along towards the center. Not entirely accurate, because the individual sunspots last no more than tens of days, but the effect that takes place dragging the magnetic field along as the sun rotates is the cause of this effect. And so we have this 11-year cycle. At the height of the 11-year cycle, the sun becomes very, very active, and a number of things happen. Certainly in that time, we have a large number of sunspots, and that's true, but also we have larger and larger effects. Effects larger than sunspots are referred to as prominences, where eruptions are taking place on the surface of the sun to such a great extent that large numbers or large quantities of charged particles are being ejected from the surface of the sun. Sometimes there are associated with this are large explosions taking place on the surface of the sun at the height of sunspot activity that are called coronal mass ejections. Mass from the surface of the sun is ejected out into space, has very, very high energy, and travels through space. And in particular, some of these coronal mass ejections can arrive at Earth. Well, as the mass ejection travels through space, it has its own magnetic field associated with it. It's not regular, uniform, and easy to diagram like the Earth's magnetic field. It's all crazy in different directions as the mass ejection travels through space. When it arrives at Earth, its magnetic field combines with the magnetic field of the Earth, and it causes a significant disturbance. These are called geomagnetic storms, when the magnetic field of the Earth is significantly disrupted. The charged particles associated with the coronal mass ejection are scooped up by the Earth's magnetic field, and we see a lot of borealis activity, both at the north and south pole of the Earth, as the charged particles from the sun are captured and spiral in, oscillating at very high frequency, where they begin to emit visible light that we see in the sky as the aurora borealis. And so during the 11-year cycle, periods of high sunspot activity, when the sun is active, large quantities of charged particles are available, we see that increase in solar sunspot activity. Collecting the charged particles that come from the sun and observing all of the sun's behavior throughout its solar cycle gives us key information that we can study to understand the dynamics of stars, our sun being only one of the billions and billions and billions of stars in our universe.